Hey everyone, and welcome back to the channel. Today we're diving deep into one of Earth's most spectacular and powerful phenomena, volcanic eruptions. But we're not just talking about any old eruption. We're exploring a fascinating, sometimes explosive trigger that many people don't even know about, the mixing of different magma types. You might think magma is just magma, right? Well, it's a lot more complex and dynamic than you'd imagine. And this complexity can lead to some truly dramatic events. Imagine a volcano as a giant underground plumbing system. Deep beneath the surface, there are chambers filled with molten rock, or magma. But here's the kicker. These chambers aren't always connected, and the magma inside them isn't always the same. Think of it like having different types of paint in separate buckets. Now, what happens when you start mixing those paints? Sometimes you get a new, interesting color. Other times you get a chemical reaction, maybe even a fizz or a burst of energy. In volcanoes, magma mixing can be a literal recipe for disaster, or rather, for an eruption. So, what exactly is magma mixing? It's when two or more distinct batches of magma, often with different chemical compositions, temperatures, and gas contents, come into contact and interact with each other within the Earth's crust. This isn't just a gentle stirring. It can be a violent encounter that dramatically changes the properties of the magma system. Think of a hotter, less viscous magma rising from deep within the Earth and encountering a cooler, more evolved magma sitting closer to the surface. It's like pouring hot coffee into cold milk. You get turbulence, temperature changes, and new chemical reactions. Let's talk about why these differences are so important. Magma can vary wildly. Some are rich in silica, making them very viscous, thick and sticky like honey. These often have a lot of dissolved gases trapped within them, like champagne. Others are low in silica, making them more fluid and runny like warm syrup, and they typically have fewer trapped gases. When these two very different magmas meet, things get interesting. One of the biggest impacts of magma mixing is on viscosity. If a hotter, less viscous magma injects into a cooler, more viscous magma, it can lower the overall viscosity of the resident magma. This might sound counterintuitive, but think of it this way. The hotter magma acts like a lubricant, making the whole mixture flow more easily. And what happens when magma becomes less viscous? It can move upwards more quickly, increasing pressure within the conduit. But that's not the only way mixing acts as a trigger. Temperature contrast is another massive factor. When a hot magma body mixes with a cooler one, the cooler magma heats up. This might seem minor, but it can be crucial. Heating can cause minerals within the cooler magma to melt, changing its composition and, importantly, releasing dissolved gases that were previously trapped. Imagine superheating a carbonated drink. The bubbles come out much faster and more violently. The sudden exsolution, or release of these gases, dramatically increases pressure within the magma chamber, propelling the magma upwards with incredible force. This rapid gas release is a game changer. Gases like water vapor, carbon dioxide, and sulfur dioxide are dissolved in magma under immense pressure deep underground. As magma rises and pressure decreases, these gases start to form bubbles. When hot, fresh magma mixes with cooler, gas-rich magma, the temperature increase and compositional changes can accelerate this bubble formation and expansion. It's like shaking a soda bottle, then suddenly opening it. The rapid expansion of gas creates an explosive eruption. We also see chemical interactions at play. When magmas of different compositions mix, they don't just blend, they can react. This can lead to the formation of new minerals, which in turn can alter the magma's physical properties. Sometimes, this interaction can lead to a sudden decrease in the magma's ability to hold dissolved gases, forcing them out rapidly. Think of it like adding an ingredient to a chemical solution that causes it to suddenly fizz and overflow. These chemical shifts can destabilize the entire system, paving the way for an eruption. Let's look at some real-world examples. Many historically explosive eruptions are now understood to have been triggered by magma mixing. Mount St. Helens, for instance, in its 1980 eruption, showed clear evidence of magma mixing, with signatures of both dacitic, silica-rich, and andesitic, less silica-rich, magmas. Geologists can study the composition of volcanic rocks, like crystals and glass, after an eruption to piece together the story of what happened in the magma chamber. The presence of specific minerals or zoning patterns in crystals can indicate that they grew in different magma environments before being mixed together. Another classic example is the Soufrière Hills volcano on Montserrat. Its long-term eruption has frequently shown evidence of magma mixing events preceding significant explosive phases. Scientists monitor these volcanoes closely, and understanding magma mixing is a critical part of forecasting eruptions. If instruments detect seismic activity that suggests new magma is ascending, and there are signs of compositional changes, it can be a strong indicator of an impending mixing event and potential eruption. So, how do geologists figure all this out? It's truly detective work. They analyze volcanic rocks, examining minerals under microscopes and using sophisticated chemical analysis tools. They look for things like compositional zoning in crystals, where the outer layers have different chemistry than the core, indicating growth in different magma batches. They also study the textures of the rocks, looking for evidence of incomplete mixing, like enclaves of one magma type within another. This field of volcanology is constantly evolving. Scientists use experimental petrology, where they recreate high-pressure, high-temperature conditions in the lab to see how different magmas interact. They also develop complex computer models to simulate magma chamber dynamics and how mixing might lead to an eruption. This research is vital because understanding the specific triggers for eruptions helps us to better predict them and, ultimately, to protect communities living near active volcanoes. The next time you see a powerful volcanic eruption, remember that it's not always just a single batch of magma rising to the surface. It could be the dramatic culmination of a cosmic dance deep underground, where different magma types meet, mingle, and sometimes explode. It's a testament to the incredible forces at play within our dynamic Earth. Thank you so much for joining me on this journey into the fiery heart of our planet. If you found this explanation intriguing, please hit that like button, share this video with your friends, and don't forget to subscribe for more fascinating insights into Earth science. Your support really helps the channel grow. See you next time.